An oil drop carrying 6 electronic charges. That means charge on the oil drop is negative and equal to 6 electronic charges. Okay. So minus 6 into 1.6 into 10 raised to the power minus 19 coulomb is the charge on some oil drop, having a mass of 1.6 into 10 raised to the power minus 12 gram. So mass of this oil drop is 1.6 into 10 raised to the power minus 12 grams. That means 1.6 into 10 raised to the power minus 15 kilogram. Okay, so mass is this. Falls with some terminal velocity in a medium. So this particular oil drop is falling with some terminal velocity. That means it is falling with uniform speed. Let us assume that that particular speed is v with terminal velocity in a medium. What magnitude of vertical electric field is required to make the drop move upwards with the same speed as it was formerly moving downwards with? Ignore buoyant force. So we have to ignore the buoyant force. That means we have to consider only the force of viscosity of the medium, because in case of terminal velocity, suppose the oil drop has got mass m, so weight of the oil drop is acting vertically downward, and since it is moving downward, so force of viscosity acting on the oil drop would be F, and force of viscosity is proportional to the velocity of the body. Force of viscosity of the medium, the drag force the medium can apply, is always proportional to the velocity. That means whatever its value is, that is according to the velocity. So this is the first case. So in case of terminal velocity, this drag force of the medium must be equal to the weight of this oil drop. Okay. Now we have to apply the electric force with the help of electric field, vertical electric field, so that it may start moving vertically upward with the same speed. So just consider this drop to be moving upwards with the same speed v. mg must be acting as it is. There is no change in the direction of the weight. Velocity this time is upward, so drag force must be opposite to the velocity. So drag force must be vertically downward. And what should be its magnitude? The same as that in the previous case, because velocity is same in both the cases. So it has to be uniform velocity, the terminal velocity. That means we require electric force in vertical upward direction. Let it be Q into E. Capital E will be the electric field intensity. So this is the electric force. If this electric force can balance these two, then this oil drop will start moving upward with velocity v, with the terminal velocity v. So in this case, we can write equation as Q E equal to mg plus F. So now using these two equations, first is F is equal to mg and another is this thing. So let us put the value of F in this particular equation. So what we have now is QE is equal to 2 times mg. Okay. So what is required here is the electric field. So we can now calculate the electric field intensity, which is equal to 2 mg divided by the charge. So here we have everything ready to substitute, and if you substitute all these, then you will get 10 divided by 3 into 10 raised to the power 4 Newton per coulomb. So it will be the electric field intensity which is required for this oil drop to move vertically upward with the same velocity as it was previously falling in the same medium. So common thing in these two cases is the drag force of the medium. So here you can see that option C should be the correct option. 10 by 3 is 3.3 into 10 to the power 4 Newton per coulomb.